According to the strictest laws of physics, you should not exist. The screen you're watching this on should not exist. The entire universe should be nothing but a cold, empty void filled with nothing but light. When the Big Bang happened 13.8 billion years ago, it should have been a suicide pact. It created matter, the stuff you and I and the stars are made of, and it created antimatter, its volatile evil twin. The rules of energy are very clear on this. You cannot create one without the other. They come in pairs, and when those two meet, they destroy each other instantly. The math says they should have been created in equal amounts, cancelled each other out completely, and left absolutely nothing behind. But clearly, the math was wrong. You are here. The universe is full of heavy, stable matter. We are the survivors of a cosmic accident that we cannot explain. For 80 years, we have been asking why matter won the war. Why are we the leftovers? And now, deep underground at CERN, on the border of France and Switzerland, we are finally getting an answer. But it is not coming from a giant collider smashing things together. It is coming from a darker, quieter place where scientists have trapped the ghost. They are putting antimatter in magnetic bottles, keeping it alive for months, dropping it to test gravity, and even driving it around in trucks to shoot it at radioactive targets. They are finding tiny, impossible cracks in the laws of reality. Cracks that suggest our existence might just be a lucky mistake in the code of the universe. So, what exactly is happening with antimatter at CERN? Why does it refuse to play by the rules? And is this mystery finally pointing us toward a new force of nature that we have missed for 100 years? To understand why this is such a massive problem, you have to understand what antimatter actually is. And I do not mean the sci-fi version. I do not mean the fuel for starships or the bomb in a Dan Brown movie. I mean the real, physical substance that we manufacture every single day. Antimatter is not magic. It is engineering. We use it in hospitals all the time. If you have ever heard of a PET scan, that stands for positron emission tomography. The positron is the antimatter version of the electron. When doctors use that machine, they are literally using antimatter to look inside your body. But what makes it different from normal matter? Imagine looking at your hand in a mirror. The reflection looks exactly like your hand. It has the same shape, the same size, the same skin texture. But everything is flipped. Your left side becomes the right side. In physics, antimatter is that mirror image. For every fundamental particle that makes up your atoms, there is a twin. Take the proton. It sits in the center of every atom in your body, and it has a positive electric charge. Its mirror twin is the antiproton. It has the exact same mass as a proton. It spins the exact same way. If you weighed it, it would weigh the same, but it has a negative electric charge. Take the electron, it buzzes around the outside of the atom with a negative charge. Its twin is the positron, which has a positive charge. On paper, they look like siblings. They are perfect counterparts. Nature loves symmetry, and this is the ultimate symmetry. Positive and negative. Matter and antimatter. If you built a car out of antimatter, it would look like a car. It would drive like a car. The engine would run. But there is one deadly rule that makes this relationship impossible. Matter and antimatter can never, ever touch. Because if they do not just bump off each other like billiard balls. They do not just bond like chemicals. They vanish, and they take the surrounding area with them. This process is called annihilation, and it is the most violent, efficient, and absolute force in the known universe. To understand the scale of it, think about burning wood. When you light a fire, you are converting matter into energy. But it is messy. You get ash, you get smoke, you get charcoal. You are only converting a tiny, tiny fraction of the wood's mass into heat. It is incredibly inefficient. Now step it up to a nuclear weapon. In a nuclear explosion, like the ones that destroyed cities in the 20th century, we are splitting atoms. It is terrifyingly powerful. But even that is wasteful. In a nuclear bomb, Only a small percentage of the uranium or plutonium is actually converted into pure energy. The rest is just blown apart as radioactive debris. Antimatter is different. When an electron meets a positron or a proton meets an antiproton, there is no ash. There is no smoke. There is no debris. There is no leftover. The conversion is 100%. The mass of both particles disappears completely, and according to Einstein's famous equation, energy equals mass times the speed of light squared. That mass is instantly transformed into energy, usually in the form of high-energy gamma rays. It is a perfect erasure, a cosmic undo button. If you shook hands with your antimatter doppelganger, the resulting explosion would be thousands of times stronger than the Hiroshima bomb, just from the mass of your two bodies. This is why handling it is such a logistical nightmare. You cannot put antimatter in a jar. If it touches the glass, it explodes. You cannot put it in a metal tank. If it touches the walls, it explodes. It doesn't matter what the container is made of, because the container is made of matter, and matter is the enemy. To keep it, to hold it, you have to suspend it in nothingness. You have to use invisible magnetic fields to levitate it in a vacuum that is emptier than outer space. It is like trying to hold a drop of pure acid that burns through absolutely anything it touches. So if this stuff is so volatile, and if it annihilates perfectly with matter, why aren't we exploding right now? Why are we sitting here, made of matter, on a planet made of matter, in a galaxy made of matter? This is where the paradox begins. Let's rewind the clock all the way back. 13.8 billion years ago. The Big Bang. In that first fraction of a second, the universe was incredibly hot and incredibly dense. It was pure energy. And as it expanded and cooled, that energy started to freeze out into particles. It started to create stuff. Now, here is the rule of the game. Physics tells us that energy turns into matter and antimatter in equal pairs. You cannot create a proton without creating an antiproton. It is like digging a hole in the ground. You create a pile of dirt, which is matter, and a hole, which is antimatter. You cannot create the pile without the hole. So, in the beginning, the universe should have been 50% matter and 50% antimatter. A perfect balance. But remember what happens when they touch? In that dense, hot, early universe, particles were crammed together so tightly that they couldn't avoid each other. Matter and antimatter would have been constantly colliding. Create, annihilate, create, annihilate. It should have been a frenzy of destruction. The two sides should have waged a war of total erasure until absolutely nothing was left. The matter pile should have filled the antimatter hole perfectly back to zero. By all logical predictions, the universe today should be nothing but a bath of leftover radiation. No stars, no planets, no life, just a glowing, empty soup of photons. But look around. We are here. And we know the antimatter isn't hiding somewhere else. If there were galaxies of antimatter out there colliding with galaxies of matter, we would see giant glowing borders in the sky where the annihilation was taking place. We have looked with our best telescopes. The sky is dark. The antimatter is gone. The mirror cracked. The game was rigged. This mystery is called the Baryon Asymmetry, and it basically means that in the first moments of the universe, a war was fought between matter and antimatter, and it was a massacre. Almost everything was destroyed. 99.9% of all the stuff that was created in the Big Bang was annihilated instantly. The universe effectively hit the delete button on itself, but it missed a spot. For every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. Just one. A tiny, insignificant imbalance. A rounding error in the cosmic accounting books. When the Great Annihilation happened, the billion pairs cancelled each other out. They turned into light. That light is still visible today. We call it the cosmic microwave background radiation. It is the echo of that ancient battle. But that one extra particle, the one that didn't have a partner to dance with, the one that didn't have a mirror twin to destroy it, it survived. And that lone survivor is you. Every atom in your body, every rock on Earth, every star in the Milky Way, all of it is just that tiny, leftover fraction. We are the survivors of a near-perfect apocalypse. We are the error that the universe couldn't correct. And honestly, this is embarrassing for physics. Because according to the standard model, the best theory we have, this shouldn't be possible. The laws of physics are supposed to treat matter and antimatter almost exactly the same. There is no reason written in the fundamental code of reality why matter should have won. Did matter cheat? Did antimatter break? Was there some hidden force that tipped the scales just enough to let us live? For decades, we have been looking for the fingerprint of this event. We have been smashing particles together at the Large Hadron Collider, looking for any sign that matter and antimatter behave differently. We have found hints, small clues, but nothing big enough to explain the existence of an entire universe. The math still doesn't add up. We are missing a huge piece of the puzzle, and that brings us to today, to CERN, where scientists have decided that if smashing particles won't give us the answer, maybe trapping them will. Maybe we need to look at the survivors' dark twins closely. Maybe we need to put them in a cage, hold them still, and ask them why they lost. So we have a universe full of matter survivors. But the first question a skeptic might ask is simple. Are we sure the antimatter is gone? Could it be hiding somewhere else? The universe is a big place. Maybe the Big Bang did create a 50-50 split, but somehow the two sides got separated. Maybe our galaxy is made of matter, but the Andromeda galaxy next door is made of antimatter. Or maybe there are vast clusters of antimatter galaxies billions of light years away, completely cut off from us. It sounds like a reasonable theory. It would save the symmetry of the laws of physics. But there is a reason astrophysicists do not believe it. The problem is the boundaries. Space is not truly empty. The space between galaxies is filled with thin gas, dust, and stray particles drifting in the dark. If a galaxy made of matter was sitting next to a galaxy made of antimatter, the gas clouds on their edges would touch. And we know exactly what happens when they touch. Annihilation. The border between those two galaxies would be a war zone. It would be glowing with a very specific, high-energy light called gamma radiation. We have satellites orbiting the Earth right now, like the Fermi Gamma Ray Space Telescope, that are scanning the sky for exactly this signal. We have looked at the edges of galaxy clusters. We have looked at colliding gas clouds. We have looked all the way back to the cosmic microwave background, and we see nothing. The universe is frighteningly quiet. There are no glowing walls. There are no annihilation borders. As far as we can see, and we can see almost back to the beginning of time, everything seems to be made of the same stuff as us. Matter dominates completely. Antimatter is not hiding in some distant corner. It has been wiped out. This absence is what drives physicists crazy. It is like walking onto a battlefield after a massive war and finding only one army standing, with zero trace of the enemy bodies. Just gone. So, we have to assume the asymmetry is real. The laws of physics must contain a hidden preference, a bias. Somewhere in the deep code of the universe, there must be a line that says matter is allowed to stay, but antimatter must leave. But finding that line has turned out to be the hardest scavenger hunt in the history of science. To understand how we even know this stuff exists, we have to go back to 1928, to a British physicist named Paul Dirac. He was trying to solve a puzzle. He wanted to combine two new, radical theories of his time: quantum mechanics, which describes the tiny world of atoms, and special relativity, which describes things moving near the speed of light. He wrote down an equation to describe the electron. It was a beautiful, elegant equation. But it had a problem. You know how in basic math, the square root of 4 can be 2, but it can also be minus 2? Because minus 2 times minus 2 is also 4? Dirac's equation was doing something similar. It was spitting out two solutions for the energy of the electron. One solution described the normal electron perfectly. Negative charge, positive energy. Normal. But the second solution described a particle with negative energy. At the time, that sounded like nonsense. Energy cannot be negative. It is like saying you have a height of -6 feet or a speed of -50 miles per hour. Most physicists would have just ignored it. They would have said it was a math quirk, a glitch, and thrown it away. Dirac did not throw it away. He looked at the math and he made a bold, almost arrogant prediction. He said that this was not a mistake. He said this particle is real. He claimed there must exist an anti-electron, a particle with the same mass as an electron, but with a positive charge, a mirror twin. People thought he was reaching. But just 4 years later, in 1932, an American physicist named Carl Anderson was looking at tracks of cosmic rays in a cloud chamber. A cloud chamber is just a box filled with supersaturated vapor. When a charged particle flies through it, it leaves a trail of mist, like a jet plane leaving a contrail in the sky. Anderson saw a track that looked exactly like an electron, but it curved the wrong way in the magnetic field. It turned left instead of right. It was the positron, Dirac's ghost particle. It was the first time in history that a human being discovered a new piece of reality just by trusting the math on a piece of paper. Antimatter was not an invention. It was not a theory anymore. It was a discovered fact. And suddenly the universe got twice as complicated. Because if the electron has a twin, then everything must have a twin. So if antimatter is real, but the universe is empty of it, where do we find it? The answer is surprising. It is raining down on you right now. Nature still makes antimatter. It just does not keep it around. High-energy particles from exploding stars and black holes, which we call cosmic rays, are smashing into the Earth's upper atmosphere constantly. When they hit the air molecules, they create a shower of debris, a cascade of new particles, and among those particles are antiparticles, mostly muons and positrons. They rain down on you every second. Some of them pass right through your body. Some of them hit the roof of your house and annihilate. It is happening all the time, but the amount is so tiny and they are moving so fast that you never notice. It is like a light drizzle in a hurricane. We also see it in radioactive decay. Take a banana. Bananas are rich in potassium-40, a radioactive isotope. Every 75 minutes or so, a banana on your kitchen counter spits out a single positron. Yes, your fruit bowl is technically an antimatter source. But here is the catch. That positron flies out, travels maybe a fraction of a millimeter, hits an electron in the air or the peel, and zap, gone. A tiny flash of gamma rays that is too weak to hurt you, but real enough to measure. This is the problem with studying antimatter in the wild. It is fleeting. It is born, it lives for a nanosecond, and it dies the moment it touches anything real. To study it, to really understand it, we cannot just wait for a banana to decay. We cannot just catch random drops of rain from the sky. We need a lot of it. We need a concentrated beam. We need to be able to poke it, prod it, and weigh it. And for that, we cannot rely on nature. Nature is too messy. We have to build it ourselves. And that process is one of the most difficult engineering challenges humanity has ever faced. We have actually become pretty good at making antimatter, but there is a catch. The cost is astronomical. I mentioned PET scans earlier. In those machines, we create positrons to look for tumors. But we create them one by one, and they exist for a tiny fraction of a second before they annihilate inside the patient. That is easy. But if you want to make a chunk of antimatter, if you want to make enough to hold in a jar, the difficulty spikes vertically. The quantity we make is pathetic. If you took all the antimatter ever created in the history of humanity, all the particle colliders, all the labs since 1932, and you put it all together in one pile, you would not even have enough to boil a cup of tea. We are talking about nanograms. Why? Because it is insanely inefficient to produce. To make 1 gram of antimatter, you would need to run the Large Hadron Collider for millions of years. You have to put in billions of times more energy than you get out. NASA once estimated the cost of producing 1 gram of antihydrogen at about $62.5 trillion. That is 62 trillion. For a thimbleful, it is, by far, the most expensive substance ever known. Nothing else comes close. Not diamonds, not californium, not printer ink. So when we talk about experiments at CERN, forget the idea of industrial production. We are not making fuel for starships. We are crafting artisanal, bespoke atoms. We are making them one by one, counting them like precious jewels. And because they are so rare and so expensive, every single one of them matters. We cannot afford to lose them. We cannot afford to let them touch the walls. We need a place where we can keep them safe. A nursery for the most volatile babies in the universe. And that place exists. It is a concrete building in Geneva that houses a machine unique in the entire world. This leads us to the heart of the mystery. The Antimatter Factory at CERN. Everyone knows the Large Hadron Collider, the giant ring that smashes protons together to find new particles. The LHC is a discovery machine. It is a sledgehammer. It smashes things to see what falls out. But the Antimatter Factory works on the exact opposite principle. The LHC is about acceleration, speed, energy. The Antimatter Factory is about deceleration, patience, cold. Its heart is a machine called the Antiproton Decelerator, or AD for short. Here is how it works. The main accelerators fire a beam of protons into a block of metal, usually iridium. The collision is violent. It creates a spray of new particles, and among the debris are antiprotons. But these newborn antiprotons are wild. They are traveling near the speed of light. They are hot, energetic, and completely uncontrollable. If you tried to study them, they would fly right through your detector before you even blinked. You cannot study a bullet while it is flying. You have to catch it. So the AD takes these wild particles and puts them into a magnetic ring. But instead of speeding them up, it applies brakes. It tames them. It reduces their energy from nearly the speed of light down to something manageable, something catchable. And once they are slow, the real magic begins. Because now we can try to do the impossible. We can try to assemble them into atoms. We can try to build an anti-world, piece by piece, right here in the middle of Europe. But slowing them down is just the first step. To truly unlock their secrets, to find out why they are different from us, we need to do something even harder. We need to make them stand perfectly still. And that requires technology that pushes the limits of what is physically possible. Imagine trying to read the fine print on a baseball while it is being pitched at 100 miles per hour. You cannot do it. All you see is a white blur. You know it is a ball, you know it is white, but you cannot see the stitching, and you certainly cannot see the logo. To see the details, you need the ball to stop. You need to hold it in your hand. Physics is exactly the same. When particles are moving at the speed of light, their properties are smeared out by relativity and kinetic energy. We can measure their mass and their charge, sure, but if we want to find the tiny, subtle differences, the cracks in the mirror that explain our existence, we need them to be almost frozen. This is the job of a machine called ELINA. It stands for Extra Low Energy Antiproton Ring. It sounds like a nice name for a friendly aunt, but ELINA is a technological marvel inside the Antimatter Factory. It is a small, hexagonal ring that takes the already slowed antiprotons from the big decelerator and puts them into a deep freeze. The way it works is brilliant. It uses something called electron cooling. It basically injects a stream of cold electrons into the beam of hot antiprotons. The electrons are moving at the same speed as the antiprotons, but they are colder, meaning they have less random vibration. As they travel together, the hot antiprotons bump into the cold electrons and transfer their heat to them, like a hot cup of coffee cooling down when you pour in cold milk. By the time the particles leave ELINA, they are moving at just a few % of the speed of light. For a particle physicist, that is basically walking speed. They are sluggish. They are calm. And this is critical, because now, and only now, we can deliver them to the experiments. The Antimatter Factory is not just one experiment. It is a hub, like a central station. Elena sends beams of these precious, slow antiprotons to different teams of scientists, each trying to interrogate them in a different way. But they all face the same terrifying problem. Even at walking speed, an antiproton is a ticking time bomb. If it drifts just a millimeter to the left and hits the wall of the pipe, it is gone. If it hits a stray molecule of air that leaked in, it is gone. So how do you catch something that you cannot touch? How do you hold a ghost without letting it pass through your fingers? The answer is a trap. Specifically a device called a penning trap. This is one of the cleverest inventions in the history of physics, designed to create a cage without bars. If you cannot touch the particle with matter, you have to touch it with force fields. Imagine a vacuum chamber. Inside, there is absolutely nothing. No air. A vacuum better than deep space. Now, imagine we turn on a powerful magnetic field that points straight up. If a charged particle, like our antiproton, tries to move sideways, the magnetic field grabs it and forces it to spin in a tight circle. It is like a marble rolling around in a bowl. It cannot climb out to the left or right. It is stuck in a spiral. But it can still move up and down, right? It could escape out the top or the bottom of our magnetic bowl. So we add an electric field. We put metal caps at the top and bottom of the chamber and charge them with negative voltage. Since the antiproton has a negative charge, and like charges repel, it hates those caps. When it tries to fly up, the electric field pushes it back down. When it tries to fly down, the field pushes it back up. The result is levitation. The particle is trapped. It is bouncing up and down, spinning in a circle, floating in the middle of nowhere, held in place by invisible hands. We can keep a single antiproton in a penning trap for months. We actually did that once. The scientists gave it a name and checked on it every day like a pet. But a lone antiproton is not enough. An antiproton is just the nucleus. It is just the center. To make real antimatter, to make an anti-atom that mimics the stuff we are made of, we need to give it a partner. We need to build anti-hydrogen. Hydrogen is the simplest atom in the universe. One proton, one electron. So anti-hydrogen is one antiproton and one positron. It sounds simple to make, like snapping two Lego bricks together. But it is a nightmare. You have to take a cloud of antiprotons, which are negative, and a cloud of positrons, which are positive, and mix them together gently enough that they capture each other and form an orbit, but not so violently that they just fly past each other or annihilate. It is like trying to get two dancers to catch each other while they're both skydiving in a hurricane. The experiment that masters this dance is called Alpha. The scientists there are essentially cosmic matchmakers. They take the antiprotons from Elena and positrons from a radioactive source, cool them both down to near absolute zero, colder than the empty space between galaxies, and then gently merge the two clouds. When it works, the positron falls into orbit around the antiproton. Success. You have created an atom of antihydrogen. This is a historic achievement. We are not just smashing things anymore. We are building. We are doing chemistry with antimatter. But the moment you create antihydrogen, you have a new, terrifying problem. Remember the penning trap? It worked because the antiproton had an electric charge. The magnetic and electric fields could grab onto that charge and hold it. But an atom of antihydrogen is neutral. The negative charge of the antiproton and the positive charge of the positron cancel each other out. The net charge is zero. The trap stops working. The invisible walls disappear. Suddenly, the anti-atom is free. It can drift in any direction it wants, and gravity starts to pull on it. It starts to fall, or float, or drift towards the wall, and the moment it touches the wall, flash, annihilation. For years, this was the heartbreaking reality of antimatter physics. You would spend hours making these atoms, and then microseconds later, they would vanish because you couldn't hold them. The Alpha team had to invent a completely new kind of trap. A magnetic minimum trap. It relies on the tiny, tiny magnetic spin of the particle itself. It is extremely weak. It is barely strong enough to hold anything. It is like trying to hold a bowling ball with a single thread of spider silk. But it worked. In 2011, they trapped antihydrogen for over 1,000 seconds. Almost 20 minutes. That was the game changer. Because if you can hold it for 20 minutes, you can interrogate it. You can shine lasers on it. You can poke it. And most importantly, you can drop it. This brings us to one of the most embarrassing questions in physics. A question so simple a 5-year-old could ask it. But until last year, no Nobel Prize winner could answer it with certainty. Does antimatter fall down? I know. It sounds like a joke. It sounds like something from a cartoon, where the character floats away when they drink the wrong potion. You might say, of course it falls down. Gravity is gravity. Einstein's general relativity relies on something called the weak equivalence principle. It says that gravity pulls on everything equally, regardless of what it is made of. A feather, a hammer, a planet, or an antimatter atom, gravity should treat them all the same. If antimatter fell up, if it had anti-gravity, it would break Einstein's theory. It would shatter our understanding of the universe. It would mean you could build perpetual motion machines. It would mean the energy conservation laws are wrong. It would be chaos. So, 99.9% of physicists were sure it falls down. But in science, being sure is not good enough. You have to measure it. You have to look. And nobody had ever seen antimatter fall. Why? Because gravity is weak. Think about it. You can pick up a paperclip with a tiny fridge magnet, defeating the gravity of the entire Earth. Electromagnetism is billions and billions of times stronger than gravity. For a charged particle like an antiproton, stray electric fields in the lab completely overwhelm gravity. It is like trying to hear a whisper at a rock concert. The electrical noise is just too loud. That is why we needed neutral antihydrogen. Neutral atoms do not care about electric fields. They only feel the magnetic trap and gravity. So, the Alpha team built a new machine, Alpha G. The G stands for gravity. It is basically a tall, vertical vacuum tube, a slide for antimatter. The plan was simple: make a cloud of antihydrogen, hold it in the magnetic trap, and then turn the magnets off, open the cage, and see which way the birds fly. In late 2023, they finally did it. It sounds easy to say they turned off the magnets, but the engineering required is some of the most difficult on Earth. You are trying to measure a force, gravity, that is insanely weak. The magnetic force holding the particles is trillions of times stronger than the gravity pulling them down. To make this work, the scientists at Alpha had to balance the magnetic fields with the precision of 1 part in 10,000. Think about that. It is like trying to weigh a feather while it is sitting on top of a roaring jet engine. You have to subtract the force of the engine perfectly, so that only the weight of the feather remains. If the magnetic field at the top of the trap is even slightly different from the field at the bottom by a microscopic amount, it will push the antimatter up or down, and you will think it is gravity. You will get a false result. So, they initiated the sequence. Inside the trap, a cloud of antihydrogen atoms was bouncing gently. Slowly, they lowered the magnetic walls. Imagine the magnetic trap like a bowl. The atoms are rolling around in the bottom. Now, imagine you start to make the bowl flatter and flatter. Eventually, it becomes a flat table. At that moment, the atoms are free. If they are weightless, they should float out the top and bottom in equal numbers. If they have negative gravity, if they fall up, they should mostly drift out the top. If they obey Einstein, they should fall out the bottom. They ran the test over and over. Count the flashes on the walls, and the answer is, it falls down. Antimatter accelerates downwards at roughly 9.8 meters per second, squared, just like regular matter, just like a rock, just like you. There was a collective sigh of relief across the physics community. Einstein survives another day. Anti-gravity is still science fiction. But wait, Do not consider the question answered yet, because the result was not perfect. The measurement had an error margin of about 20%. That means we know it falls down, but we do not know if it falls exactly as fast as matter. And in that 20% gap, a lot of strange things can still hide. So here is where we stand in the investigation. We are stuck in a logical dead end, and it is a very expensive, very high-tech dead end. We have looked at the Big Bang models, and the math says we should have been annihilated instantly. We have looked at the cosmic microwave background for evidence of antimatter galaxies hiding in deep space, and the data says they are not there. We have built the most precise traps in human history, cooled atoms to within a whisper of absolute zero, and dropped them to see if they fall up. And gravity, stubborn, boring gravity, says no. They fall down just like everything else. When you have eliminated the external possibilities, you have to look at the internal ones. We have eliminated the idea that matter and antimatter are separated by space. We have mostly eliminated the idea that they react to gravity differently. So, what remains? There is only one possibility left. It is the most uncomfortable possibility of all. It implies that there is something wrong with the particles themselves. It implies that an antiproton is not perfectly an antiproton. It implies that the reflection in the mirror has a scar that the original face does not have. If we want to solve this mystery, we have to stop looking at where the particles are going, whether they are falling down or flying left, and start looking at what they are. We have to look at their internal identity. We have to look at the rules of symmetry that govern their existence. Because if the universe is not perfectly symmetrical, if the laws of physics actually change depending on who is following them, then we have to rewrite the rulebook. To do that, we have to talk about mirrors. Not the glass ones in your bathroom, but the mathematical mirrors that hold reality together. We need to go deep into the quantum world. And I have to warn you, down here, common sense does not just leave the room. It runs away screaming. Imagine you are playing a game of chess. The rules are simple. Pawns move forward, bishops move diagonally. Knights jump in an L shape. These rules are absolute. They do not change if you play the game in New York or in Tokyo. They do not change if you play in the morning or at night. And most importantly, they do not change if you swap the white pieces for the black pieces. If the white player can move a knight in an L shape, the black player can also move a knight in an L shape. The game is symmetrical, it is fair. Physics is supposed to be the same way. We believe, or at least we want to believe, that the laws of the universe are invariant. They should not care about arbitrary things. If I do an experiment here, and you do the exact same experiment on the moon, we should get the same result. That is called translation symmetry. If I do an experiment today, and you do it tomorrow, we should get the same result. That is time translation symmetry. These symmetries are the bedrock of science. If they did not exist, we could not learn anything, because the rules would keep changing on us. But when it comes to matter and antimatter, the game of chess gets much more complicated. Physicists have identified 3 specific ways you can flip the board. 3 fundamental symmetries that are supposed to keep the universe fair. We call them C, P, and T. C stands for charge conjugation, which is swapping matter for antimatter. P stands for parity, which is flipping left and right. T stands for time, which is running the clock backward. For a long time, we thought these 3 mirrors were unbreakable. We thought that if you applied any of them to the universe, the physics would look exactly the same. We thought nature was perfectly balanced. But as we probe deeper into the atom, we started to realize that nature might actually be cheating. The game might be rigged. And the first clue did not come from antimatter. It came from a simple cobalt atom, and a woman who decided to check if the universe knew its left hand from its right. Let's break down these mirrors, because this is where the magic happens. First, consider P-symmetry or parity. This is the spatial mirror. It flips all the spatial coordinates. Left becomes right. Forward becomes backward. Think about looking at a clock in a mirror. In the real world, the hands move clockwise. In the mirror, they move counterclockwise, but, and this is the key point, the mechanism still works. The gears still turn. The laws of mechanics do not care if the clock is running lefty or righty. If you watched a video of a billiard game in a mirror, you would not be able to tell it was a reflection. The balls bounce off the walls at the same angles. Gravity pulls them down the same way. There is no handedness to gravity or electromagnetism. For centuries, scientists assumed that parity was perfect. Why would the universe care about left and right? They are just human concepts. Empty space does not have a left side. It seemed obvious. It seemed logical. But quantum mechanics has a nasty habit of destroying things that seem obvious. In the mid-20th century, two theoretical physicists named Tsung-Dao Lee and Chen-Ning Yang started looking at the weak nuclear force. This is the force responsible for radioactive decay, the process where an atom spits out a particle and changes into something else. They noticed something funny. Nobody had ever actually proven that the weak force obeys parity. Everyone just assumed it did because all the other forces did. So they asked a brilliant experimentalist named Chien-Shiung Wu, known as the First Lady of Physics, to test it. They asked her to check if the universe had a favorite hand. They wanted to know if a radioactive atom would behave differently if you looked at it in a mirror. And what she found shocked the entire scientific world. The year is 1956. Madame Wu sets up an experiment using atoms of cobalt-60. Cobalt-60 is radioactive. It decays by shooting out an electron, a process called beta decay. To make the test work, she had to cool the atoms down to near absolute zero so they would stop jiggling around from heat. Then, she applied a strong magnetic field to line up their nuclei. Think of the atoms like tiny spinning tops. The magnetic field forced them all to spin in the same direction, pointing up. Now, here is the test. If the universe is symmetrical, if the spatial mirror is perfect, then the electrons should shoot out in all directions equally. Or at least, they should shoot out the top and the bottom of the spinning atom in equal numbers. It should not matter which way the atom is spinning. Physics should be blind to direction. But that is not what happened. When Madame Wu turned on the experiment, she saw that the electrons were almost exclusively shooting out of one side. Specifically, they were shooting out in the direction opposite to the spin. It was as if the atoms knew which way was south. Imagine you have two machine guns. One is a normal gun, the other is a mirror image gun. If you pull the trigger on the mirror gun, the bullet should not come out the back of the barrel. But in Wu's experiment, it essentially did. The result was undeniable. The weak nuclear force violates parity. It is 100% asymmetric. It turns out that neutrinos, those ghostly particles that fly through the Earth, are always left-handed. There are no right-handed neutrinos in nature, and antineutrinos are always right-handed. The mirror was shattered. If you looked at the universe in a mirror, you would know it was a reflection immediately. Because in the reflection, the left-handed neutrinos would become right-handed, and the weak force would stop working. The reflection would be a broken, dead universe where stars might not burn the same way. This discovery was a trauma for physics. It meant that space itself is not neutral. It meant that left and right are woven into the fundamental fabric of reality. This discovery sent physicists into a panic. The idea that nature had a preference for left over right was disturbing. It felt wrong. It felt ugly. So, physicists, being optimists, tried to save the situation. They said, okay, the spatial mirror is broken. That is bad. But maybe if we combine the mirrors, we can fix it. Here was the logic. We know that parity, the spatial mirror, is broken because the universe prefers left-handed particles. We also suspected that charge symmetry, the matter-antimatter mirror, might be broken in the weak interaction. But what if they are broken in opposite ways? What if the left-handedness of matter is perfectly balanced by the right-handedness of antimatter? Think about it. A neutrino is left-handed. An anti-neutrino is right-handed. So if you take a neutrino, flip its charge to make it an anti-neutrino, and flip its parity to make it right-handed, you get a real, working particle. It is like a double negative, minus times minus equals plus. This was the birth of CP-Symmetry. The C stands for charge and the P stands for parity. Physicists decided that the true mirror was not just P, and it was not just C. It was the combination of both. The theory said that if you take any process in the universe, swap matter for antimatter, and view it in a mirror, it will look exactly the same. This restored order. It meant that symmetry was safe. It meant that matter and antimatter were still, fundamentally, equal partners. They just had opposite-handedness. It was a beautiful idea. It saved the elegance of the standard model. It meant that the laws of physics were still fair, as long as you applied the double filter. For about 8 years, everyone was happy. We thought we had solved the problem. We thought nature had just played a little trick on us with the parity thing, but that deep down, the balance was kept. But there was a problem with this perfect symmetry. If CP-symmetry is perfect, then matter and antimatter should have decayed at exactly the same rate in the early universe. They should have annihilated perfectly. If CP-symmetry is perfect, we should not exist. So there was a tension. On one hand, the theory looked great. On the other hand, the fact that we are alive suggested that the theory had to be wrong. There had to be a crack in the double mirror too. But nobody had seen it. Until 2 men went searching for it in a beam of particles called kaons. This brings us to 1964, a pivotal year in the history of physics. The location was Brookhaven National Laboratory in New York, and the scientists were James Cronin and Val Fitch. They were studying a particle called the neutral kaon. Kaons are fascinating, strange little particles produced in high-energy collisions. They are unstable and do not live very long, but they have a unique property that makes them perfect for testing the laws of the universe. A neutral kaon can turn into its own antiparticle and back again. It oscillates. It is like a pendulum swinging between being matter and being antimatter. Now, according to the strict rules of CP-symmetry, the double mirror we thought was unbreakable. These kaons were divided into 2 distinct types based on how they decayed. One type was short-lived, and the other was long-lived. The rule said that the long-lived kaon was absolutely forbidden from decaying into 2 pions. It was only allowed to decay into 3 pions. Think of it like a strict traffic law. If you are a heavy truck, you must take the highway. You are never, ever allowed to take the side street. If CP-symmetry is perfect, that rule should never be broken. Not once. Not in a billion years. But Cronin and Fitch decided to set up a traffic camera on the side street just to be sure. They built a detector at the end of a long beam line, waited for all the short-lived particles to die off, and then watched the surviving long-lived kaons. They were looking for the impossible. They were looking for the 2-pion signature, and after analyzing thousands of events, they found it. It was incredibly rare. It happened roughly once in every 500 decays. But it was there. The kaons were breaking the rule. They were taking the side street. This innocent-looking decay proved that the long-lived kaon and its antiparticle were not perfectly symmetrical. They were distinguishing between matter and antimatter. By decaying into 2 pions, they were showing a physical preference that violated CP-symmetry. This was a shock to the system. It meant that the double mirror was cracked. It meant that even if you swap matter for antimatter and flip left for right, the universe still looks different. The laws of physics have a bias. They have a built-in preference for one outcome over the other. For a moment, physicists were ecstatic. They thought they had found the answer. They thought this tiny crack in the kaon decay was the reason we exist. The reason matter won the war against antimatter. But when they sat down to do the calculations, the celebration stopped cold. The effect was real, but it was far too small to explain the universe. The discovery of CP violation in kaons was a triumph for experimenters, but it was a disaster for theorists. They had a broken law of physics and no way to explain it. At the time, In the 1960s and early 70s, we only knew about 3 types of quarks: up, down, and strange. The math of the time was rigid. When you tried to write down the equations for how these 3 quarks mixed and interacted, the math simply did not allow for CP violation. The symmetry was locked in. You could not break it without breaking the whole theory. The equation was like a 2-dimensional flat sheet of paper. You cannot tie a knot in a flat sheet of paper. You need a 3rd dimension. In 1973, 2 Japanese theorists named Makoto Kobayashi and Toshihide Masukawa proposed a radical solution. They said that if the math does not allow for symmetry breaking with 3 quarks, maybe there are more quarks that we haven't found yet. They calculated that if there were 3 generations of quarks, meaning 6 quarks in total, then the math would open up. The flat sheet of paper would become a 3-dimensional shape. With 6 quarks, the mixing matrix, which describes how quarks transform into each other, acquires a complex phase. In plain English, it allows for a twist in the fabric of the theory. This twist permits matter and antimatter to behave differently. It was a bold prediction because, at the time, nobody had ever seen a 4th, 5th, or 6th quark. They were inventing new particles just to fix a math problem. But they were right. The charm quark was found soon after. Then the bottom quark in 1977. And finally the top quark in 1995. The 6 quark model was confirmed, and Kobayashi and Masukawa won the Nobel Prize. This mechanism, now known as the CKM matrix, explains perfectly why the kaons violate symmetry. It fits the data like a glove. But here is the frustrating part. Even with 6 quarks, even with this beautiful complex matrix, the amount of asymmetry it produces is still pathetic. It explains the kaons, but it does not explain us. If the CKM matrix were the only source of asymmetry in the universe, there would be roughly 1 extra particle of matter for every 10 billion pairs. That is not enough to build galaxies. We need an effect that is 1 billion times stronger. So, the standard model works, but it fails to answer the biggest question. We have found a penknife, but we are looking for the bazooka that shaped the cosmos. To understand exactly what we are looking for and why the current theories are failing us, we need to look at a checklist created by Andrei Sakharov. In 1967, Sakharov, who was a brilliant nuclear physicist, wrote down the absolute requirements for creating a universe made of matter from a Big Bang that started as neutral energy. He treated it like an engineering problem. He said, if you want to bake a cake called the material universe, you need exactly 3 ingredients. If you miss even one, the cake collapses, and you end up with an empty void. Here is the recipe. Ingredient 1 is baryon number violation. This means there must be a process that can turn pure energy into protons without creating an equal number of antiprotons. We have never seen a proton decay, and we have never seen this process in a lab. But we assume it must exist at incredibly high energies. Ingredient 2 is C and CP violation. This is what we have been talking about. The laws of physics must be biased. They must treat matter and antimatter differently. If the reactions are perfectly symmetric, you just make equal piles of stuff, and they eventually cancel out. You need a process that favors the production of matter over antimatter. Ingredient 3 is thermal non-equilibrium. This is the subtle one. The process has to happen fast, in a universe that is rapidly cooling down. If everything stays hot and balanced, the reactions will just run backward and undo whatever matter you created. It is like trying to make ice. You cannot do it in a warm oven. You need a rapid drop in temperature to lock the changes in place. So, physicists look at this list and check off the items. Condition 3, the Big Bang was definitely a rapid cooling event. Check. Condition 1, we think it is possible in grand unified theories. Check. Condition 2, CP violation. This is the sticking point. We have found CP violation in the kaons and in the CKM matrix, so technically the ingredient exists. But the quantity is wrong. It is like a recipe calling for a cup of sugar, and we only have a single grain. We have the right ingredient, but not enough of it to make the cake. This tells us that there must be another source of CP violation hiding somewhere in the universe. A new particle, a new force, or a new interaction that breaks the mirror much more violently than the standard model allows. If the answer is not in the light particles like kaons, maybe it is in the heavy ones. This line of thinking led physicists to study the beauty quark, also known as the bottom quark. This is a monster of a particle. It is about 4 times heavier than a proton, and because it is so heavy, it has a lot of energy to get rid of when it decays. In quantum mechanics, having more energy means having more options. A beauty quark can decay into hundreds of different combinations of lighter particles. It is like dropping a heavy glass vase on the floor versus dropping a plastic cup. The vase shatters into 1,000 complex pieces, while the cup just bounces. That complexity is exactly what we want. The more paths the decay can take, the more chances there are for quantum interference to happen. The more chances there are for new physics to sneak in and mess with the results. Theorists realize that if CP violation is going to be strong anywhere, it is going to be strong in the decays of mesons containing a beauty quark. These are called B mesons. To study them, humanity built massive factories. In the early 2000s, we had the Bombard experiment in California and the Bell experiment in Japan. These were huge accelerators dedicated to one single purpose, making billions of B mesons and watching them die. They wanted to see if the B mesons showed a larger asymmetry than the kaons, and they did. The experiments were a success. They measured CP violation in the B system with incredible precision. But the result was bittersweet. The asymmetry was exactly what the standard model predicted. It was larger than the kaon effect, yes, but it fit perfectly within the CKM matrix theory. It was not the anomaly we were looking for. It did not break the theory, it confirmed it. This was frustrating. We built these machines to break the standard model, to find the hole in the math where the extra matter came from, and instead, the machines told us the math was solid. But physicists are stubborn. They decided that maybe we just weren't looking closely enough. Maybe we needed more data, higher energy, and a different kind of particle. So they built the LHCb experiment at CERN to take the hunt to the next level. Up until very recently, almost all our knowledge of the broken mirror came from mesons. Remember, a meson is a simple pairing of one quark and one antiquark. It is a useful laboratory, but it is not what you are made of. You are made of baryons. Protons and neutrons are baryons, made of 3 quarks bound together. If we want to explain why the universe is full of matter, we ultimately need to understand why baryons exist. For a long time, measuring CP violation in baryons was considered too difficult. The collisions are messy, the data is noisy, and the events are rare. But the Large Hadron Collider changed the game by producing sheer brute force quantities of data. The LHCb experiment, which specializes in analyzing heavy particles, began sifting through the debris of billions of collisions looking for a specific particle called the lambda B baryon. This is an exotic cousin of the neutron. Instead of being made of up-down-down quarks, it is made of up-down beauty. It is unstable and decays in a fraction of a second. In 2017, and with confirming data arriving in recent years, LHCb observed the first clear evidence of CP violation in the decay of the lambda B baryon. They watched it decay into a proton and 3 pions, and they compared it to the decay of the anti-lambda B. And they saw a difference. The angles at which the particles flew out were not the same. The rates were not the same. The matter version and the antimatter version were following different paths. This is a historic milestone. It is the first time we have clearly seen symmetry breaking in a baryon, the same class of particles that makes up the stars and our bodies. It proves that the mechanism for creating a matter-dominant universe can work in baryons. It is a proof of principle. But, and this is the recurring theme of our story, the size of the effect is still consistent with the standard model. It is still not the massive, universe-shaping anomaly we need, It is just another piece of the puzzle that fits too well. We are in a strange position where we keep finding cracks in the mirror, but every time we measure the crack, it is exactly the size the textbooks say it should be. It is maddening. We are walking around a house knowing there is a secret room somewhere, tapping on every wall, finding hollow spots, but never finding the hidden lever that opens the door. We need to look deeper. We need to look for something forbidden, something that shouldn't happen at all. But before we assume the standard model is perfect and unbreakable, we need to look at the messy corner of the data where things refuse to fit for a long time. For about 5 years, the physics world was obsessed with a glitch in the B-meson data at CERN. It involved a rule called Lepton Flavor Universality. I know, that sounds like a terrible flavor of ice cream, but the concept is actually incredibly simple. It is about fairness. The standard model says that the weak nuclear force should be blind. It should treat electrons and muons exactly the same. Think of it like a vending machine that accepts two types of coins: a nickel, the electron, and a dime, the muon. The muon is basically just a heavy electron. It has the same charge, the same spin, it just weighs 200 times more. But the vending machine shouldn't care about the weight. If you put in a nickel or a dime, the mechanism should work the same way. The machine should dispense the decay products 50% of the time for electrons, and 50% of the time for muons. That is the law. It is written in the bedrock of physics. But when scientists looked at the decay of billions of B-mesons, the machine started jamming. It was spitting out electrons just fine, but it was eating the muons. The ratio wasn't 1-to-1, it was off by about 15%. The muons were disappearing. This wasn't just a small rounding error. This was a screaming anomaly. It sat there in the data, year after year, daring us to explain it. This glitch suggested that there was a hidden force in the universe, something we had never seen before, that was specifically targeting the heavy muons and pulling them out of the equation. It felt like we had found a secret door. Theorists went wild. They started writing papers about leptoquarks and Z-prime bosons, new particles that could explain the bias. We thought this was it. We thought the standard model had finally cracked. We thought we had caught the universe cheating at its own game. And then, the floor fell out from under us. This is the brutal, heartbreaking reality of working at the cutting edge of science. You have to be willing to kill your own darlings. In late 2022, the team at LHCb finished a massive update. They didn't just look at the numbers again. They tore the entire experiment apart and rebuilt the analysis from the ground up. They added millions of new collisions from the latest run of the collider. They recalibrated the sensors to account for misidentified particles. They checked every cable, every line of code, every background signal. They wanted to be absolutely 100% sure that the missing muons were real. And when they finally ran the new, cleaner numbers, the anomaly evaporated. It just vanished. The ratio snapped back to a perfect 1-to-1. The electrons and muons were being treated equally after all. The vending machine was working fine. We were just counting the coins wrong. It turns out we were victims of a massive statistical fluke. It is like looking at a cloud and seeing a face. You swear it is a face. You can see the eyes, the nose, the mouth. You call your friends over and say, "Look at the face," but then the wind shifts, the cloud moves, and the face dissolves back into random fluff. That is what happened here. The Lepton anomaly was a mirage, and I cannot overstate how frustrating this is. You might think scientists want their theories to be right, but actually, we want the standard model to be wrong. Finding out that it works perfectly is the worst possible news. It means we are back to square one. It is like a zombie that refuses to die. Every time we think we have shot it, every time we think we have found a hole in its armor, it gets up and heals itself. So now, we are left standing in the wreckage of our hopes, with a perfect theory that explains everything, except the one thing we actually care about: why we exist. So, the easy answers are gone. The anomalies are dead. We are now at a literal crossroads. We know the answer to the antimatter mystery is out there, but our current tools are hitting a wall. We need to try something drastic, something that sounds almost stupid. Let's look at the map of CERN. On one side of the campus, we have the Antimatter Factory. It is a clean, quiet, precise facility. It produces the coldest, most perfect antiprotons in the world. We can trap them, we can hold them, we can make them sit still. But we can mostly only do simple tests there, like checking their color or dropping them. It is like a high-end pastry kitchen. On the other side of the campus, hundreds of meters away, there is a facility called Isolde. This place is a factory for monsters. It produces exotic radioactive atomic nuclei that do not exist in nature. Nuclei with too many neutrons. Nuclei that are deformed, shaped like pears instead of spheres. These radioactive atoms are bursting with strange nuclear forces. They are the spicy, volatile ingredients. Theorists believe that if we could put an antiproton inside one of these radioactive nuclei, the interaction would be explosive in terms of data. It would peel the nucleus apart layer by layer and reveal secrets about the strong nuclear force that we cannot see any other way. It is the perfect experiment. The beauty meets the beast. But there is a massive logistical problem, a geography problem. Why can't we just connect the two labs with a pipe? It seems obvious, right? Just shoot the antimatter down a tube. But we cannot. The magnetic fields required to guide the particles would interfere with other experiments. The vacuum would be impossible to maintain over that distance without leaks. And you cannot move the massive radioactive factory to the antimatter factory. So, you are left with one insane option. You have to box up the antimatter. You have to disconnect the magnetic trap from the wall, put it on a set of wheels, and physically drive it down the street like a pizza delivery. This leads us to Project PUMA. The name stands for Antiproton Unstable Matter Annihilation. It sounds like the plot of a heist movie, but it is real. They are building a portable antimatter trap. Think of it like a high-tech thermos, but instead of keeping coffee hot, it keeps 1 billion antiprotons suspended in a magnetic vacuum while being bounced around on the back of a truck. Do you realize how crazy that is? In a normal lab, we freak out if the temperature changes by 1 degree. Now, they want to unplug the experiment, load it onto a vehicle, and drive it 400 meters through the real world. They have to deal with speed bumps. They have to deal with the vibration of the engine. They have to deal with the gravity shifts as the truck goes up and down slopes. Inside the PUMA trap, there is a double zone system. A storage zone to keep the particles safe, and a collision zone for the science. To make this work, the vacuum inside must be perfect. Better than deep space. If even a few molecules of Swiss air leak in during the drive, the antimatter will annihilate before it arrives. And the magnetic field must be rock solid, powered by batteries that cannot fail. If the power cuts out for a microsecond, the magnetic cage collapses, the antimatter hits the wall, and the experiment is over. Now, don't worry. It's not a nuclear bomb. The amount of antimatter is small, nanograms. If it explodes, it won't destroy Geneva. It won't even blow up the truck. But it will destroy the experiment. It will destroy months of work and the billion precious particles that took weeks to harvest. Why take this risk? Why go to all this trouble just to move a few atoms across the street? Because if PUMA works, it breaks the chains of the laboratory. It means antimatter is no longer stuck in the factory where it was born. It becomes mobile. And if it becomes mobile, the possibilities are endless. We could take it to other labs. We could maybe one day take it to space. So let's say the truck makes it. Let's say we get the antimatter to the radioactive lab without spilling the soup. What happens next? What exactly are we hoping to see when we fire an antiproton at a radioactive nucleus? We are looking for something called the neutron skin. In a normal atom, like the ones in your body, protons and neutrons are mixed together fairly evenly. They clump in the middle. But in these exotic radioactive atoms, there are too many neutrons. They get pushed to the outside. They form a skin, a halo around the core. This skin is pure nuclear matter. It is the same stuff that neutron stars are made of. But it is incredibly hard to measure because the strong nuclear force is so messy. It is like trying to measure the thickness of an orange peel without cutting the orange. Enter the antiproton. When an antiproton approaches this nucleus, it acts like a smart missile. It has a negative charge, so it gets sucked in by the positive nucleus. But it doesn't just crash into the center. It tends to spiral around the outside first. It skims the surface, and eventually it finds a proton or a neutron on that outer skin and annihilates with it. Boom. A precise explosion on the surface. This explosion throws out pions, which act like shrapnel. By measuring that shrapnel, scientists can calculate exactly how thick the neutron skin is. Why does that matter? Because if we understand the skin of an atom, we understand the skin of a neutron star. We understand the density of the universe. And more importantly, this annihilation event is a stress test. It is a violent interaction that pushes the laws of nuclear physics to the breaking point. And remember, we are still looking for cracks. We are looking for places where the standard rules fail. Maybe in the wreckage of that tiny portable annihilation, we will find a debris pattern that shouldn't be there. Maybe the radioactive monster has a secret that the stable atoms don't. This is the hope of PUMA. To use the rarest substance on Earth to unlock the secrets of the strangest matter in the universe. If the PUMA experiment succeeds, it does something much bigger than just measuring the skin of a neutron star. It fundamentally changes the way we do physics. Think about how we have done science for the last 100 years. If you want to study something dangerous or exotic, like antimatter or a deadly virus, you have to build a massive, immovable fortress to contain it. You bring the scientist to the experiment. You are tethered to the wall socket. It is like the early days of computers. In the 1950s, if you wanted to use a computer, you had to travel to a university, walk into a room the size of a gymnasium, and stand inside the machine. You couldn't take it with you. PUMA is the moment antimatter goes from being a mainframe computer to being a laptop. It cuts the cord. And once you cut the cord, the possibilities explode. Imagine if we could take a trap full of antiprotons, not just to another building at CERN, but to a different country. What if we could take it to a laboratory deep underground, shielded from cosmic rays where the background noise is zero? What if we could take it to a space station? Antimatter is the most sensitive sensor we have ever created. It reacts to absolutely everything. If we can make it mobile, we can use it to map the invisible structures of the universe in ways we cannot even imagine yet. We could use it to test materials for future fusion reactors. We could use it to probe the nature of dark matter. We are moving from the era of manufacturing antimatter to the era of deploying it. But there is a catch. There is always a catch. Even with this mobile technology, even with the trucks and the traps and the lasers, we are still stuck with the same fundamental problem that has haunted us since the beginning of this story. We are building better and better tools to measure a universe that refuses to give up its secret. We are like cartographers drawing a map of an island that keeps changing shape every time we blink. We have mobility now, but do we have the right destination? While the engineers are driving trucks, the theorists are going back to the chalkboard to ask a more disturbing question. What if the answer isn't in the particles at all? What if it is in the empty space between them? We tend to think of a vacuum as nothingness, empty, boring. But in quantum physics, a vacuum is not empty. It is a frothing, boiling ocean of energy. Virtual particles pop in and out of existence faster than you can blink. Fields vibrate and fluctuate. It is alive. Some physicists believe that the explanation for why matter won the war lies in a fifth force that lives in this vacuum. We know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. That is the standard quartet. But who says there are only 4? What if there is a 5th one? A force so weak that we have never noticed it, but just strong enough to tip the scales in the early universe. Imagine a force that only talks to antimatter, or a force that pushed matter and antimatter apart just moments after the Big Bang, segregating them before they could annihilate. We are hunting for particles that might carry this force. We call them things like dark photons or axions. These are the ghosts in the machine. They are theoretical whispers. If they exist, they would explain everything. They would explain the missing antimatter. They would explain dark matter. They would fix the math. But finding them is a nightmare. It is like trying to listen for a single falling leaf in the middle of a heavy metal concert. We are building experiments now that are not looking for collisions, but are looking for silence. We are building shielded boxes and waiting for a dark photon to wander in and jiggle an atom. It is a long shot. It is a gamble. But when you have ruled out everything else, the invisible ghosts are the only suspects left. We have to ask ourselves, are we missing the forest because we are looking too closely at the trees? Are we missing the fifth force because we are too obsessed with the other four? Let's zoom out for a second and look at the scoreboard. It is not looking good for the new physics team. We have thrown everything we have at the universe. We dropped antimatter to see if gravity is weird. It fell down normally. We smashed beamisons to see if they break the rules. The anomaly vanished. We measured the shape of the electron to see if it was lopsided. It was perfectly round. Every single time we tried to find a crack in the standard model wins. It is infuriatingly perfect. You might think this is a success story. Human beings wrote down a set of equations in the 1970s, and 50 years later, they still predict every single experimental result to 12 decimal places. It is the greatest intellectual achievement in history. But to a cosmologist, this perfection is a disaster. It is a straitjacket. Because we know the standard model is incomplete. We know it for a fact. It does not explain gravity, it does not explain dark matter, and it absolutely 100% does not explain why you are here. It does not explain the Baryon Asymmetry. So we are in a crisis. We have a theory that works perfectly in the lab, but fails completely to explain the universe outside the window. It is like having a map of a city that shows every single street, every manhole cover, and every building perfectly, but it completely forgets to include the people. We are the people. We are the missing variable, and the fact that our machines are confirming the theory instead of breaking it means we are stuck. We are trapped in a local maximum of understanding. We have climbed to the top of a hill, and the view is great, but we can see a much higher mountain in the distance, and we have no idea how to get there. We are waiting for a revolution. We are waiting for something to break. And maybe, just maybe, the thing that needs to break is not a particle, but a fundamental law of logic. There is one final wall we haven't smashed yet. One final mirror that we believe is unbreakable. It is called CP-Symmetry. We talked about C, charge, P, parity, and T, time separately. We know nature violates C. We know it violates P. We even know it violates the combination CP. But the holy grail, the bedrock of all modern physics, is the combination of all three. CPT. The theorem states that if you take the entire universe, turn all the matter into antimatter, flip it in a mirror, and run time backward, the result must, absolutely must, be indistinguishable from the original universe. This isn't just a suggestion. It is a mathematical necessity built into the structure of relativity and quantum mechanics. If CP-Symmetry is broken, then the theory of relativity is wrong. If CPT is broken, causality, the idea that cause comes before effect, might be wrong. It is the load-bearing pillar of reality. If you pull it out, the whole house collapses. And that is exactly why scientists are attacking it. Experiments like BASE at CERN are comparing the magnetic moments of protons and antiprotons with insane precision, down to parts in a billion. They are looking for the tiniest difference. If they find that an antiproton spins just slightly faster than a proton, or weighs slightly different, it would mean CPT is broken. It would be the end of physics as we know it. It would mean we have to rewrite Einstein. It would mean the universe is not just strange, but fundamentally alien to our logic. Most physicists are terrified of this possibility. It is the nuclear option. But when you are desperate, when you have exhausted every other option, and the mystery of existence is still staring you in the face, you start eyeing the nuclear button. You start asking, are we willing to destroy our understanding of the universe in order to explain why we are living in it? But what if we are wrong? What if we are looking at this whole problem backward? What if there is no deep, hidden reason for matter winning the war? What if it was just luck? This brings us to the most controversial idea in science, the anthropic principle. Imagine a lottery. The odds of winning are 1 in a billion. It is almost impossible. But if 1 billion people buy tickets, someone will win. Now imagine that winner standing on stage holding the giant check, screaming, "Why me? Why did the universe choose me? There must be a reason. There must be a law of physics that made my ticket special." But there isn't. It was just statistics. Someone had to win, and he is the only one around to ask the question. The losers aren't there to ask why they lost. Maybe our universe is like that. Maybe there is a multiverse. Maybe there are billions of other universes bubbling up in the cosmic foam. In some of them, antimatter won. In some of them, matter and antimatter annihilated perfectly, leaving nothing but light. In those universes, there are no stars, no planets, and no people to make YouTube videos about physics. They are empty, silent wastelands. We are here asking these questions simply because we are in the one rare universe where a random fluctuation allowed matter to survive. We are the lottery winners. It is not satisfying. It feels like a cheat. We want a reason. We want a hero to the story, not just a roll of the dice. But the universe does not owe us a satisfying narrative. It only owes us existence. And right now, as we stand in front of our giant machines, scratching our heads at the perfect data, we have to confront the possibility that we are nothing more than a statistical fluke, a lucky accident in an infinite casino. But is that true? Or is that just giving up? Now, let's step away from the deep philosophy for a moment and talk about the thing everyone secretly wants to know. If antimatter is so powerful, if it releases 100% of its mass as pure energy, when do we get the warp drives? When do we get the starships that can fly to Mars in a week? It is a fair question because the math is incredibly seductive. To understand why, you have to look at energy density. Think about the gasoline in your car. It is a chemical fuel. When you burn it, you are breaking chemical bonds, which releases a little bit of heat. It is okay for driving to the grocery store, but for space travel, it is pathetic. It is like trying to power a train by burning marshmallows. Next up the ladder is nuclear fission, the stuff in power plants and submarines. That is much better. It releases thousands of times more energy than gas. But even nuclear fission only converts about 0.1% of the fuel's mass into energy. It is still leaving 99.9% of the potential power on the table. Antimatter is the end of the line. It is the physics maximum. When matter and antimatter annihilate, the conversion is 100%. 1 gram of antimatter contains the same amount of energy as the atomic bomb dropped on Hiroshima. Just 1 gram. A piece the size of a raisin. If you could harness that, you wouldn't need massive tanks of rocket fuel. You could travel to the nearest star, Proxima Centauri, in decades instead of thousands of years. It is the holy grail of propulsion. So, why aren't we doing it? Why are we still using chemical rockets that look like glorified fireworks? The problem is not the engine. The problem is the fuel tank. Remember, you cannot touch antimatter. You have to hold it in a magnetic trap. To hold even a gram of charged antimatter, the magnetic pressure required would be so immense, it would rip the walls of the spacecraft apart. The magnets would weigh more than the ship itself. And if you make neutral antihydrogen, you cannot hold it with strong magnets at all. Plus, if your containment system fails for even a microsecond, if a fuse blows or a battery dies, your fuel tank doesn't just leak. It becomes a nuclear weapon that vaporizes you instantly. We are currently like cavemen who have discovered jet fuel, but are trying to carry it around in a wicker basket. The potential is there, the physics is valid, but the engineering gap is so wide it might as well be the Grand Canyon. But does that mean it is impossible? Not necessarily. We just have to stop thinking about carrying huge tanks of it. There is another massive problem with the antimatter dream that science fiction rarely mentions. It is the problem of the bank account. In physics, there is no such thing as a free lunch. You cannot create energy out of nothing. To create antimatter, we have to use the formula E equals mc squared in reverse. We have to take a huge amount of energy, E, and turn it into mass, m. And the exchange rate is terrible. It is the worst currency exchange in the universe. To create a single antiproton at CERN, we have to smash protons into a metal target with incredible force. But most of that energy doesn't turn into antimatter. It turns into heat, light, noise, and other useless particles. The efficiency is something like 1/10000000th of 1%. Think of it like this. Imagine you want to charge a single AA battery. But to charge that one battery, you have to burn down an entire forest. That is how we make antimatter today. We pump enough electricity into the accelerators to power a small city, and at the end of the year, we have produced maybe a few nanograms of antiprotons. If you wanted to make that 1 gram we talked about for the Starship, it would cost roughly $60 trillion, and it would take the current CERN facility millions of years to produce it. We are putting in 1,000,000 units of energy to get 1 unit back. As a fuel source, it is mathematically bankrupt. It is an energy storage medium, not an energy source, and it is the most inefficient battery ever invented. So whenever you see a headline saying, NASA is building an antimatter engine, be very skeptical. Unless we find a natural source of antimatter, like harvesting it from the radiation belts around the Earth or scooping it up from solar flares, we are never going to use it for mass propulsion. It is just too expensive. It is like trying to build a house out of diamonds. Sure, it would be a very strong house, but where are you going to find the bricks? This reality check is important because it grounds us. It reminds us that antimatter at CERN is not about industrial power. It is about knowledge. We are not making it to burn it. We are making it to read it. We are paying that $60 trillion price tag because the information hidden inside those atoms is worth more than the energy we lose creating them. But let's not be total pessimists. Just because we can't build a starship doesn't mean antimatter is useless. There is one place where the destructive power of annihilation is actually a good thing, inside the human body. Specifically, in the war against cancer. Right now, the gold standard for treating deep tumors is radiation therapy. We blast the tumor with X-rays or protons, but X-rays are stupid. They are like a carpet bomb. They burn the skin on the way in, they burn the healthy tissue around the tumor, and they burn the organs on the way out. They damage everything in their path. Proton therapy is better. Protons are like bullets that stop at a specific depth. You can tune them to stop right inside the tumor, delivering most of their energy where it counts. This is called the Bragg peak, but antimatter offers something even better. Imagine firing a beam of antiprotons into a tumor. Like protons, they can be tuned to stop exactly at the cancer site. But when they stop, they don't just sit there. They annihilate. They connect with the protons in the cancer cells and explode on a microscopic level. This explosion does two things. First, it releases a massive burst of energy locally, destroying the DNA of the cancer cells far more effectively than any X-ray. It is a surgical sniper shot. Second, and this is the cool part, the annihilation shoots out gamma rays that escape the body. These gamma rays act like a beacon. They tell the doctors exactly where the beam is hitting. It is real-time feedback. You can see on a screen exactly which cells you are destroying while you are destroying them. CERN has actually run experiments on this, called the ACE experiment, antiproton cell experiment. They found that antiprotons are 4 times more effective at killing hamster cells than regular protons. It works. The challenge, of course, is the logistical nightmare we talked about earlier. You can't put a particle accelerator in every hospital. You can't easily transport the antimatter. But remember Project PUMA? Remember the truck? If we can make antimatter mobile, if we can put it in a bottle, suddenly this idea isn't so crazy. We could have a central factory making the medicine and trucks delivering the antimatter doses to clinics. It is a long way off, but it is a beautiful irony. The same substance that represents total destruction could one day be the ultimate tool for healing. As we come to the end of this journey, I want you to step back and think about what this asymmetry really means. We humans are obsessed with symmetry. We love it. We put symmetrical faces on magazine covers. We build symmetrical buildings like the Taj Mahal. We look for patterns where the left side matches the right side. We equate symmetry with beauty and perfection. And for thousands of years, we assumed the universe felt the same way. We assumed that God, or the laws of nature, or whatever you want to call it, was a geometer who loved perfect balance. But the story of antimatter teaches us the exact opposite. It teaches us that perfection is dead. If the universe was perfect, if the Big Bang produced a perfectly symmetrical 50-50 mix, it would have been a disaster. The matter and antimatter would have shook hands, annihilated, and left nothing but a boring bath of light. No stars, no atoms, no biology, no consciousness. We exist solely because the universe is flawed. We are the children of a broken mirror. We are here because of a tiny, ugly, asymmetric scar in the laws of physics that allowed 1,000,000,001 particles to survive, while 1,000,000,000 others died. This changes how we should feel about the cracks we are hunting for at CERN. We shouldn't be frustrated that the standard model is breaking. We should be relieved. We should celebrate the anomaly, because that anomaly is us. It is a profound philosophical shift. Usually in science, we look for the rule, but here the most important thing is the exception to the rule. We are looking for the wobble in the spinning top. We are looking for the stutter in the speech. And even though we haven't found the exact mechanism yet, whether it's the neutrino mass, or a new boson, or the structure of the vacuum itself, we know it is there. The proof is not in the detector. The proof is the detector itself. The proof is the hand that built it. The fact that we can stand here and ask the question is the ultimate evidence that symmetry was broken. We are the living, breathing proof of the flaw. So, what is the conclusion? What is happening with antimatter at CERN? The honest answer is, we are stuck. But we are stuck in the most exciting place possible. We have ruled out the easy answers. We know it's not hiding in space. We know gravity probably isn't the culprit. We know the current standard model explains a little bit of the asymmetry, but not enough to build a universe. We are standing on the edge of a cliff, staring into the fog. But look at the tools we have built to pierce that fog. We have the Large Hadron Collider, still smashing particles, still hunting for the heavy ghosts of new physics. We have the Antimatter Factory, chilling atoms to near absolute zero to measure their heartbeat. We have PUMA, the audacious plan to put antimatter on a truck and drive it to a radioactive firing range. We are attacking the problem from every angle: high energy, high precision, and high risk. This is not a story about failure. It is a story about the stubbornness of curiosity. We could have stopped at the electron. We could have stopped at the proton. We could have accepted that matter just is, but we didn't. We looked in the mirror and realized something was missing, and we won't stop until we find it. Maybe the answer will come tomorrow from a wiggle in a graph at LHCb. Maybe it will come in 10 years from a gravity experiment. Or maybe it will come from a young student watching this video right now who realizes that we have been looking at the problem upside down. The universe is a puzzle box. We have found the corners. We have found the edges. But the centerpiece, the piece that explains why there is something instead of nothing, is still missing. And until we find it, the hunt continues. Because in the end, we are not just studying antimatter. We are studying our own origin story. We are trying to remember how we survived the fire. We have talked a lot about keeping matter and antimatter separate to stop them from exploding. That is rule number 1, right? Don't cross the streams. But there is a group of scientists at CERN, the Asakusa team, who looked at that rule and decided to break it. They asked a question that sounds suicidal. What happens if we mix matter and antimatter together, but we do it in a way that prevents them from touching immediately? Is it possible to build a hybrid atom? A half-breed? The answer, incredibly, is yes. They created something called antiprotonic helium. Here is how you build it. You take a normal helium atom, which has a nucleus and 2 electrons buzzing around it. Then, you fire a slow antiproton at it. If you aim it just right, the antiproton knocks one of the electrons out of the atom and takes its place. Now, pause and visualize this. You have a positive nucleus in the center. You have 1 normal electron buzzing around, and orbiting right there with it, in the same atom, is an antiproton. Matter and antimatter sharing the same living room. Normally, the antiproton would crash into the nucleus instantly and annihilate. But the laws of quantum mechanics act like a referee. They force the antiproton into a very high, stable orbit, far away from the nucleus. It is like a planet orbiting a star, safe for a few fleeting microseconds. To a physicist, a microsecond is a lifetime. It is long enough to shoot lasers at this Frankenstein atom and measure the gap between the matter and the antimatter with insane precision. Why would we build such a monster? Because this hybrid state allows us to measure the mass and charge of the antiproton relative to the electron with much higher accuracy than if it were alone in a trap. We are using the normal matter as a ruler to measure the antimatter. It is a dance of death. The antiproton is spiraling inward, getting closer and closer to the nucleus every nanosecond. The scientists have to take their measurement before the inevitable happens. It is the ultimate ticking clock experiment. And so far, even in this intimate, dangerous embrace, the matter and antimatter look perfectly symmetrical. The antiproton is exactly as heavy as the proton. It fits into the atom exactly as the math predicts. The monster behaves perfectly. While Asakusa is building hybrids, another experiment called BASE is trying to break the mirror by looking at something much smaller: the spin. Imagine a spinning top. It spins on its axis. If you put that spinning top in a magnetic field, it will wobble. This wobble is called precession. The speed of that wobble depends exactly on the magnetic properties of the particle. It is a unique fingerprint. The BASE experiment is essentially a competition. In one trap, they have a single proton. In another trap, they have a single antiproton. They set them both spinning. And then they watch. They watch for days, weeks, even months. They're counting the wobbles. If CP-Symmetry is perfect, if the universe is truly a mirror image, then the antiproton must wobble at exactly, and I mean exactly, the same speed as the proton. If the antiproton wobbles even a billionth of a percent faster or slower, it means the mirror is cracked. It means antimatter is fundamentally different. This is the most precise comparison of matter and antimatter ever made by humans. The precision is 12 decimal places. That is like measuring the circumference of the Earth and getting it right to within the width of a human hair. How do they do it? They developed a system to store antiprotons for more than a year without losing them. They keep the trap so perfect that the particles just sit there, spinning in the dark, waiting for us to find a flaw. And what have they found? Zero difference. To 12 decimal places, the tops spin at the exact same speed. The magnetic moment is identical. On one hand, this is a triumph of engineering. We have confirmed the standard model to a level of accuracy that was unimaginable 50 years ago. On the other hand, it is a cage. Every time we add another decimal place of precision and find no difference, the room for new physics gets smaller. We are squeezing the mystery into a tinier and tinier box. But we have to keep squeezing. Because if the difference is hiding in the 13th decimal place, and we stop at the 12th, we will miss the key to the universe. Let's zoom out. We have been obsessed with the idea that the missing antimatter disappeared. But what if it didn't? What if it transformed? There is another huge mystery in physics that we haven't talked about yet. Dark matter. We know that 85% of the matter in the universe is invisible. It doesn't give off light, it doesn't reflect light, but it has gravity. It holds galaxies together. We have no idea what it is. Is it possible that the two mysteries are connected? Is it possible that the Baryon Asymmetry, the missing antimatter, and dark matter are actually two sides of the same coin? Some theorists are proposing a wild idea called asymmetric dark matter. The story goes like this. In the Big Bang, matter and antimatter were created, and they annihilated, just like we thought. But maybe the extra antimatter didn't just vanish. Maybe it decayed into a new kind of particle that we cannot see. A dark antibaryon. If this is true, then the universe is actually balanced after all. We have the visible matter, us, on one side, and a hidden ocean of dark antimatter on the other side. We can't see it, we can't touch it, but we can feel its gravity. This would explain why the universe seems so heavy. It would solve two problems for the price of one. It implies that right here, right now, passing through your body, there might be ghosts of the ancient antimatter, disguised as dark matter. How do we test this? We look for portals. We look for rare events where a normal particle might turn into a dark particle, or vice versa. Experiments at CERN like Na-64 are firing beams of electrons and looking for missing energy that disappears into the dark sector. If we find a connection, it would be the plot twist of the century. It would mean the antimatter isn't gone. It is just hiding in the shadows, holding the galaxy together. It changes the picture from a survivor story to a ghost story. We aren't alone. We are just the only ones glowing in the dark. We are reaching the limits of what our current machines can do. The Large Hadron Collider is 27 kilometers around. It is a giant. But to find the heavy particles that might explain the asymmetry, to find the bazooka we talked about earlier, the LHC might be too small. We need more energy. We need a bigger hammer. This is why CERN is planning the future. They are designing a machine called the Future Circular Collider, or FCC. This thing is a leviathan. It would be a tunnel 100 kilometers in circumference, digging under Lake Geneva and the surrounding mountains. It would be big enough to encircle the entire city of Geneva and then some. Why build something so massive? Because energy allows you to time travel. The more energy you smash particles with, the further back in time you are looking. You are recreating the conditions closer and closer to the Big Bang. The LHC gets us to a trillionth of a second after the beginning. The FCC would get us even closer. It would allow us to produce billions of Higgs bosons. It would allow us to see interactions that are currently invisible. But it is a gamble. It will cost tens of billions of dollars and take decades to build. The people designing it today might be retired or dead by the time it switches on. It is a cathedral project. In the Middle Ages, stonemasons would start building a cathedral knowing they would never see the roof. They built it for their grandchildren. The physicists at CERN are doing the same. They are digging a tunnel for the next generation, hoping that that machine will be the one to finally break the mirror. It raises a question about human nature. Why do we do this? Why do we spend the GDP of a small country to find a particle that lives for a zeptosecond? It is because the alternative is unacceptable. The alternative is not knowing. The alternative is accepting that the universe is a black box that we are not allowed to open. And as a species, we hate locked doors. There is one final, slightly terrifying thought I need to leave you with regarding the stability of our universe. We have been asking why matter survived. But there is a deeper question. Is the universe even finished? We assume that the laws of physics are set in stone. We assume the vacuum of space is a stable floor that we walk on. But the study of the Higgs boson and the top quark suggests something unsettling. It suggests that our vacuum might be metastable. Think of it like a ball sitting on a ledge halfway down a cliff. It looks stable. It stays there for billions of years. But it is not at the bottom. It is not in the lowest possible energy state. There is a true vacuum further down. What does this have to do with antimatter? Everything. The precise mass of the top quark and the Higgs boson determines the stability of the vacuum. And the only way to measure those masses with perfect accuracy is to build a factory that smashes matter and antimatter together cleanly. This is one of the main goals of future colliders. If we find that the vacuum is indeed metastable, it means that at any moment, somewhere in the universe, a bubble of true vacuum could nucleate. A bubble where the laws of physics are different, where chemistry is impossible. That bubble would expand at the speed of light, destroying everything in its path. It would rewrite reality. Now, don't panic. The calculations say this probably won't happen for billions of years, if ever. But it shows how high the stakes are. We are not just collecting stamps. We are trying to understand the structural integrity of the cosmos. We are trying to read the safety inspection report of the universe. The fact that we are here, made of matter, living in a metastable vacuum, implies that we are walking a tightrope. A very thin, very lucky tightrope over an infinite drop. And the more we learn about antimatter, the more we realize just how precarious our balance really is. We are an improbability wrapped in a mystery. Let's circle back to the very beginning of this journey. We started with a simple, terrifying fact. You shouldn't be here. The math of the Big Bang predicts a universe of pure light, a perfectly symmetrical graveyard where matter and antimatter killed each other off completely. But you are here. I am here. This screen is here. We are the survivors of a cosmic purge. And now that we have looked at the machines, the lasers, and the trucks, we have to ask the question again with a new perspective. Was it just luck? Think about the margin of error we are talking about. 1,000,000,001 particles of matter for every 1,000,000,000 particles of antimatter. That is a difference of 0.0000001%. It is razor thin. If the universe had been just a tiny bit more symmetrical, we wouldn't exist. If it had been a tiny bit less symmetrical, maybe the universe would be choked with too much matter, collapsing into black holes before life could begin. We seem to be standing in a Goldilocks zone of imperfection. It is just broken enough to allow life, but not broken enough to destroy physics. Does that make you feel special? Or does it make you feel anxious? There is a concept in psychology called survivor's guilt, where people who survive a disaster ask, why me? As a species, we are asking the universe, why us? The experiments at CERN are our way of trying to find a reason. We are desperate to find a law, a rule, a mechanism that says matter had to win because of X. We want it to be inevitable. We want to believe that our existence is written into the code of reality, not just the result of a random coin toss that happened to land on heads 14 billion years ago. But the data refuses to give us that comfort. The mirror is cracked, yes, but the crack is small. Gravity is normal. The proton spins just like the antiproton. The universe is keeping its poker face, and maybe that is the ultimate lesson here. Maybe we have to accept that we are the result of a statistical fluke, a lucky roll of the dice in an infinite casino. People often ask, why are we spending billions of dollars on this? It is a fair question. We are building machines the size of cities, consuming the energy of small countries, just to find a particle that lives for a trillionth of a second. We are driving trucks of antimatter down the road. It seems absurd when we have so many problems on Earth. We have disease, we have poverty, we have climate change. Why look at the Big Bang when the planet is heating up? The answer is that fundamental science is the engine of civilization. When Paul Dirac wrote down his equation in 1928, he wasn't trying to cure cancer. He was just trying to understand the electron. He had no idea that his math would lead to the discovery of antimatter. He had no idea that 80 years later, doctors would use that antimatter in PET scans to map tumors in the human brain. He couldn't have predicted it. That is the beauty of the knowledge engine. You put curiosity in one end, and you get technology out the other, but you never know what technology or when it will arrive. The World Wide Web was invented at CERN, Not by a computer company, but by physicists who just needed a better way to share their data about particles. The superconducting magnets developed for the LHC are now used in MRI machines. The vacuum technology is used in microchip manufacturing. If we stop asking the big, useless questions about the universe, the stream of useful answers dries up. So, when you see the PUMA truck driving down the road with its billion antiprotons, don't just see a physics experiment. See the potential for a new type of medical imaging. See the potential for new energy storage materials. See the things we cannot even name yet. We don't study antimatter because we want to build starships today. We study it because we want to know how the machine works. And once you know how the machine works, you can build anything. There is a famous metaphor about scientific knowledge. Imagine our knowledge is an island in a vast ocean of ignorance. As we learn more, the island grows. But as the island grows, the shoreline, the border between what we know and what we don't know, also gets longer. The more we know, the more we realize how much we don't know. The story of antimatter is the perfect example of this. 100 years ago, we didn't even know it existed. The island was small. Then we found the positron. The island grew, but suddenly we had a new question. Where is the rest of it? Then we found the CP violation in kaons. The island grew again, but we got a new mystery. Why is the effect so small? Now we have precise traps, laser cooling, and mobile transfer. The island is huge, but the shoreline of mystery is massive. We are now asking about the stability of the vacuum, the connection to dark matter, the fifth force, and the validity of the CPT theorem. Every answer breeds 3 new questions, and this can be frustrating. We want closure. We want the final equation that fits on a t-shirt. But science is not about closure. It is about the pursuit. If the LHCb anomaly had turned out to be real, if we had found the new physics immediately, it would have been exciting, but it would have been a period. Instead, we got a comma. We got a not yet. And that not yet is what keeps the lights on at CERN. It is what drives thousands of students to study quantum mechanics. It is the friction of the unknown that creates the heat of discovery. We are mapping the coastline of a continent we can barely see. And honestly, isn't that better than already knowing everything? Isn't a mystery better than a dead end? We are standing on the beach, looking at the dark ocean, and we are building better boats. I want you to think about the sheer audacity of what we are doing. We are biological machines. We are made of carbon, water, and a few trace elements, evolved to survive on the African savanna. We are built to hunt, gather, and socialize. We are not built to understand quantum field theory, and yet, here we are, huddled in a tunnel 100 meters underground, using magnets cooled to 1.9 Kelvin, trying to trap the echo of the Big Bang. We are matter, trying to understand antimatter. It is the universe looking in the mirror and trying to understand its own reflection. There is something profoundly moving about that. When the scientists at Alpha spend nights awake waiting for a trap to cool down, or when the engineers at PUMA hold their breath as the truck goes over a speed bump, they are not just doing a job. They are carrying the torch of human curiosity. They are representing all of us. Because if we are the survivors of the Great Annihilation, if we are the lucky ones who get to exist, then we have a responsibility. We have a responsibility to not just survive, but to understand. To look at the stars and not just see lights, but to see the nuclear furnaces that forged us. To look at the empty space and see the boiling vacuum. To look at our hands and know that for every particle there, a twin died in the first microsecond of time so that we could be here. This search for antimatter is not just about physics. It is about identity. It is about figuring out our place in the cosmic story. Are we an accident? Are we a necessity? Are we alone? The machines are cold, but the intent is warm. It is the ultimate human endeavor. So, something strange is happening with antimatter at CERN. It is behaving too normally. It is refusing to give up its secrets. It is falling down when maybe it should fall up. It is spinning at the same speed as matter. It is mocking our theories with its perfect symmetry. But that silence is not empty. It is pregnant with possibility. We are pushing the doors open. We are taking antimatter out of the box and into the world. We are peeling the atomic onion. We are measuring gravity with lasers. We are rewriting the map of the possible. And even though we haven't found the bazooka yet, even though we haven't found the one big reason why we exist, we have found something else. We have found the edges of our understanding. And that is where the light gets in. The story of antimatter is far from over. In fact, with the high luminosity LHC coming online, with the PUMA project starting, with new gravity experiments ramping up, we are just finishing the prologue. The universe is broken. We know that. We are the living proof. The shattered mirror is scattered all around us. And piece by piece, experiment by experiment, we are picking up the shards and trying to glue them back together to see the true face of reality. You are the anomaly. You are the 1 in a billion. You are the impossible survivor. And as long as you are here, the question remains, why? And until we have an answer, we will keep building, we will keep smashing, and we will keep looking into the dark. Because that is what survivors do.